All right, so we're going to be starting here again. Those of you online, you should be able to hear and see the screen. The screen should say key ingredients impacting harmful algae blooms, NP ratios, as well as nitrogen and phosphorus supplies. If you have any issues online, please make sure to put the information in the chat field, and we will be keeping an eye on that. We would ask those of you online to please mute your line. We should have you muted as well. So with that, I am going to ask Dr. Joanne Burkholder, who we have flown in to share her expertise with us today. She specifically works on nutrient pollution and how it affects growth of harmful algae. So I'll let her introduce herself and go into her presentation. Thank you, Dr. Burkholder, for being here.
Thank you for inviting me. I hope everybody can hear me. Just raise your hand if you can't as I go through this talk. I was asked to give you kind of a primer on nutrient pollution, which might be a little bit late in this session, but I'm going to go ahead anyway and see if I can make sure everybody's on the same page as we move forward in trying to understand what to do to really help the Caloosahatchee system. First, I'd like to begin with this thought that there's a remarkable unity, as Val Smith wrote, a famous nutrient pollution expert in 2003, a remarkable unity is evident in the global response of algae and algal biomass to nitrogen and phosphorus availability in lakes and reservoirs, wetlands, streams and rivers, estuaries, marine coasts, in other words, across the salinity gradient. So in this presentation, I'll be talking about the Caloosahatchee system, Lake Okeechobee, but I'll also give you some examples from elsewhere because they're very applicable. In this presentation, I'll focus on the two major ingredients that are a real problem for nutrient pollution. And of course, the first one is supplies. Way too much, way in excess of the natural system for decades. That's obvious for management. But something that scientists have really gotten onto in the past decade or so and understood much better is that nitrogen to phosphorus balance ratios is also a key component in nutrient pollution, although it's often misused or overlooked completely. I really haven't heard anything about it so far in any of the discussions, for example. Most of the focus has been on supplies. And then the need to co-manage nitrogen and phosphorus, really concerted effort to co-manage both of those nutrients is needed in Florida, many Florida waters, as it is nationwide, considering both supplies and supply ratios. So those are the three components that I'll be talking about. Again, the two important aspects of nutrient pollution then are nitrogen and phosphorus supplies, the amount, you can talk about that in terms of concentration or loads, available to support algal production. It sets the total amount of algal production in the system. But the second component that's really important to understand about nutrient pollution is ratios, the balance between nitrogen and phosphorus. It sets the food quality of the entire system. That's really important and as I said, has been really overlooked for a long time. There's a natural balance concerning ratios, a natural chemical balance. Nutrient uptake ratios of rapidly growing algae, so healthy algae, tend to follow what's called the Redfield ratio. It reflects the surrounding water chemistry. And so it tells you what kind of balance the system is in terms of nitrogen and phosphorus in particular. Other chemical resources can be important, but I'll focus mostly on these two. By atoms, the Redfield ratio for nitrogen to phosphorus is about 16 to 1. In nutrient limiting conditions, I'm going to say that again. In nutrient limiting conditions, you don't have that down here. But in nutrient limiting conditions, above Redfield suggests phosphorus limitation, and it tends to be the natural background for fresh waters. And below Redfield suggests nitrogen limitation, tends to be the natural background historically for estuaries and marine coasts in general. One more thing I'd like to say to bring us all to the same point is that in terms of nitrogen and phosphorus supplies, the components, the forms of nitrogen that algae are really interested in tend to be mostly inorganic N, which I'll talk about here as the phosphate ion. They're all conditions because inorganic phosphate is highly insoluble. It sticks to everything and leaves the water column. And algae and bacteria compete for it, and they often take it up in seconds. So what you see is usually very low in terms of phosphate concentrations. And if it's not about 5 micrograms per liter or less, if it's up to 25 or 50 or 100, you have these, this study only went through 2003. I know there's been a lot of work trying to reverse this, but it keeps marching up. But beyond the total supplies, beyond total phytoplankton production as well, what about undesirable taxa? Can we move beyond chlorophyll A? You have a bad microcystis problem down here, for instance. So let me give you a couple of example studies that have been done. 102 lakes were studied in this particular example, and it was found that of all the algal groups, cyanobacteria were the most abundant at disgusting levels of nutrient pollution. So both high levels of nitrogen and high levels of phosphorus, that's who really liked it, cyanobacteria. And the dark green here indicates the maximum expected biovolume based on the data that were modeled in this study. And you can see that it's clustering toward the upper right there at the highest concentrations of total N and total P. Cyanobacteria are really nutrient loving compared to other algal groups. These big circles here indicate the maximum biovolume, and the dark bars are the 95% confidence intervals. The dashed lines are the range for 95% of the total biomass or biovolume for these different taxa that you see. And notice microcystis right up there, top 3. It really thrives in both nitrogen and phosphorus infested polluted waters. This axis on the bottom of that, I don't know if I can point to this or not, maybe not. A little bit. This is a relative axis for N and P enrichment. The other axis was for relative enrichment. It asked the question, okay, you really like both nitrogen and phosphorus, but do you prefer a little more of one than another, even though you really like them both? In terms of microcystis, again, now you see it's much lower here. To have more nitrogen than phosphorus, although especially the most nutrient-loving taxa like microcystis, you have to control both nitrogen and phosphorus. Because the species differ in their responses, you have to get both. For both abundance and microsystems was significantly higher with N in general, all these asterisks, but especially with both nitrogen and phosphorus enrichment, along with increasing temperature, caused the biggest response. Not showing that information, but the taxa were also compared in this study, and microcystis won. It had the strongest response in this treatment of NPT. Again, the authors concluded, if anyone's bothered by this chair, I can move it. The authors concluded from this study also that both nitrogen and phosphorus reductions would be needed to control cyanobacteria because of differences in taxa responses, especially with increasing climate change, which of course you folks are contending with here too. Thank you. So to encapsulate that situation in general, various studies, many others, have indicated that cyanobacteria taxa differ in their response to nitrogen and phosphorus, although they tend to win out among all the algal groups. They really love nitrogen and phosphorus pollution, but they differ in their responses to nitrogen and phosphorus depending on the balance, depending on the supplies. Some actually favor phosphorus over nitrogen, although they want them both. Some favor both equally, and some favor increased nitrogen over phosphorus, as I mentioned, Cylindrospermopsis raciborskii, for example. The production of common cyanotoxin is another problem that you contend with increasing nutrient pollution. In fact, the production geometry or balance concerns the balance of chemical resources. Again, there can be other nutrients, but I'm focusing mostly on nitrogen and phosphorus here and their interactions. and the match or the mismatch between a species or a population's requirements for nutrients and what's actually out there and available. Remember I mentioned that total phosphorus better estimates what's available to algae than inorganic phosphate, even though that's the form of phosphorus that algae take up because they store it, because they take it up so fast and so forth. Whereas inorganic nitrogen better estimates what's bioavailable to the algae from the nitrogen perspective. Dissolved inorganic nitrogen is much more strongly related to cyanobacterial biomass, usually than total nitrogen. Although management, EPA, other folks tend to think about total nitrogen more. So from a consideration of N to P ratios, the total nitrogen to phosphorus ratio, remember the Redfield ratio around 16:1 by atomic consideration. The Redfield ratio is often higher toward P limitation in subtropical freshwaters as background, such as the freshwater stretch of the Caloosahatchee may once have had. Between the total nitrogen to phosphorus ratio and cyanobacterial biomass. In other words, the lower the ratio, the more cyanobacteria, at least for some taxa, especially if high phosphorus supplies are involved in having a ratio lower. So people think about the TN to TP ratio, and of course DEP does here, EPA does, both various management folks. To be careful when you read these publications, which ratio are folks talking about? In management, it's usually this one. Some science papers and some really good ones that I'll show you a little bit of later. This ratio is also was that water column nutrient ratios mean limitation. They can be used to infer limitation. Which nutrient's limiting? Remember, if it's above the Redfield ratio, phosphorus is probably limiting. If it's below the Redfield ratio, it would be nitrogen limitation. But that was then. So in the present condition, there are two common major roles of nitrogen to phosphorus ratios. I mentioned one of them. It's so important in controlling the food quality that's at the base of the food web, because that's going to have ramifications through the entire food web. Ratio shifts cause phytoplankton dominance to shift. Same nutrient requirements, ratios as a whale that was 100 feet long, would you? Totally different than most of us and so forth. Phytoplankton are very different in their nutrient requirements depending on the taxon. There's a lot more of this oxygen problem here, hypoxia going on. And then you decide to reduce phosphorus but leave nitrogen alone, which has been going on. I'll give you a great example of that. If you reduce phosphorus and leave the nitrogen alone, then the N to P ratio should increase because the denominator is coming down. And so you end up with high inflow DIN, but lower inflow TP. And what does the system do with that? Don't forget about the sediment. Don't forget about the pumps in the sediment. That's what's going to happen. In fact, if you to try to reestablish equilibrium in the system. That phosphorus pump enhances release of stored phosphorus, and also because of the reducing conditions, the low oxygen, more ammonia coming out, quite a bit of ammonia too. And increased water column phosphorus from internal loading and major food web changes. Stoichiometric theory, this N to P ratio science would have predicted that you would get high biomass of toxic microcysts. have red fields skewed higher toward pea limitation with really low N&P supplies. But you're not asking that question. We'd settle right now for just trying to get rid of the rat infestation, right? We would really settle for trying to just make microcystis less happy. That's what we'd like to do. That's a really different question. So the paper I just mentioned talked about nitrogen-limited microcystis. That's flux, dissolved in organic nitrogen flux, was double the rate of surface inflow DIN. Sediment supplied almost 40% of what the algae wanted at the time, microcystis wanted at the time. Other work in the wet season showed that the internal DIN production actually increased with DIN loading to the estuary in the wet season. So dry season was probably the best scenario. That directly by taking up nitrogen. Studies by Pearl and others have shown that it can be influenced strongly by nitrogen additions, but it can also do it indirectly by eating cyanobacteria, Sanicococcus, that are fueled by phosphorus additions. So we're only beginning to understand the physiology of these organisms, but Karenia brevis certainly does show a hot spot in some of these areas. These authors thought that there was a big increase in Karenia blooms more recently as compared to the 1950s. They pointed out that most available nutrients end up in the bloom biomass, and so the amount of available nutrients will determine the maximum K. brevis biomass that can develop. That sounds reasonable. And they noticed that there's been a major increase in Karenia brevis along shorelines where the salinity is lower, which suggests that nutrient-rich water from land-based sources are helping to fuel the blooms, linked to large human population increases. Down in the estuarine area, we've also heard about other sources of pollution like ag in the riverine part or the freshwater part of the watershed. They noticed increased flow down the Caloosahatchee more recently than back in the 50s and suggested that that might be related to more Karenia brevis downstream during that period. This is a graph from 2018, this little cartoon. You can see the hot spot once again. And these authors interpreted their information as suggesting bacteria are plaguing the Caloosahatchee system, but the Caloosahatchee is taking a lot of nutrients